Because it's classified, or they have the skunk work project at Lockheed, they're not going to talk about. Also,
Right.
they might have reverse engineer it, and they have the TRTB and all that, but they don't have the full theory. They don't have. They cannot expand. They cannot expand. Maybe they have anti-gravity, but they cannot explain what happens, or they cannot expand the theory to new technologies. Like I do with my theory, I can not only do anti-gravity, but I expanded it to other technologies like energy teleportation, force fields, tractor beams, and things like that. So,
My guest today is Phil Bouchard. Phil was born in Ottawa, Canada, and studied mathematics and computer science at the University of Sherbrooke. He has founded his own company, which operates in the commercial software development space. Today, he's going to be discussing his theory, which is known as finite theory. And ultimately, it's a new theory to replace general relativity, but ultimately, really just extend classical physics. We're not trying to reinvent the wheel here. The theory is objective in the sense that it's predicting correct low-scale GPS gravitational and kinetic time dilation, predicting the position of the moon, predicting the perihelion precession disparity. For those that aren't aware, the perihelion is just the idea that when the Earth is orbiting the sun, it's not doing so in a perfect circle. It's actually doing so in more of an oval shape. And that oval isn't always in the same exact position, so it's sort of rotating as the Earth is rotating. We'll be discussing that, as well as predictions about gravitational light bending, even the expansion of the universe without dark energy and how that might work. He even solves black holes and the mass of the invisible universe encompassing the visible one. If you're asking yourself, what is the invisible universe? We'll be discussing that as well today. A couple things that I want to mention that we do talk about here in this interview, just to kind of give some context. So when we're talking about mass versus weight, mass is going to be the total amount of matter, or you can think of it as just stuff inside of an object. So my pencil has some amount of mass. There's some amount of stuff in this pencil, but the actual weight of this pencil is the force of this pencil due to gravity on an object. And so there's a key difference there. We're going to be discussing how weight can change and mass stays the same, which is super important when we're talking about ways to essentially negate gravity or change the weight of an object. We don't need to change the mass of an object. Of course, also, we mentioned the concept of time dilation. There are a couple of different ways that time dilation might occur. So time dilation is simply just the difference in the elapsed time that's measured by two clocks. So for example, if a clock is going much faster relative to another clock, it's actually going to start measuring time differently. If you've seen the movie Interstellar, that's a classic example. But ultimately, the movie Interstellar really focuses on the second explanation or example of time dilation, which is just as valid and just as kind of for a different scenario. That being when a clock, for example, is closer to a massive body, like a planet, it's going to measure time differently than a clock that is farther away from that body. So the satellites that we use in space, because they're further from the planet, they actually have to be accounted for this shift, this disparity in the clock measurements that they're experiencing. It was really a pleasure to speak with Phil, not just to hear about his theory, but as you're going to see, he's also presenting multiple different experiments that are able to validate his theory. And as with all of these, please do your own research. If this is interesting to you, and I'm sure it is because you're watching this, go ahead and dig into his paper as well as the videos that I will be linking his entire channel here in the description of this today. So thank you for checking this out. And without further ado, here's my interview with Phil Bouchard. So Phil, would you mind just kind of telling me your background and how you got into this theory of what you're calling finite theory. How did this begin for you?
Well, I always enjoyed astrophysics, and then I think my father was a nuclear physicist, and my brother is a chemist physicist, and me, I'm more of an astrophysicist, like addict. But um, I was always afraid to go into that field because there's not a lot of the demand is not very high. There's not a lot of jobs and things like that. So I chose computer science over astrophysics. But I always had astrophysics on the back of my mind, and also it was always for the challenge because I saw that astrophysics was kind of I felt it's a science that stagnates, you know. It's been they haven't discovered a lot of things like for the last 70 years, or they just play play pinball machines with um, the modified Newtonian physics, the superstring theory, general relativity, and they just go back and forth. They really play a pinball machine with these theories. They as soon as they find they refute one, they go back to Mond, and then they say, "Oh, Mond doesn't work," so they go back to general relativity. General relativity doesn't work, so they switch to superstring theory and things like that. And it's you know, the so there's something wrong there that has to be fixed.
And you have your own theory, which is called finite theory. Would you mind just kind of giving me a brief breakdown, sort of a 30,000 foot of finite theory? Of course, I've read your papers, but I know that not everyone has had the opportunity to do that. So would you mind just kind of breaking that down for me?
Sure. Well, first, finite theory is not a theory. It's a collection. It's a collection of laws in physics um, mangled together to create a mathematical framework that works pretty well. So I don't invent anything. It's everything I take it from existing laws and Newtonian laws and general relativity, and and I juggle the mathematics here and there, and I constructed a framework that works pretty well and is very simple to understand.
I see. And I think one of the things that's most kind of salacious per se about this theory is kind of your proposition that Einstein was wrong in his approach to general relativity. Would you mind kind of breaking down what exactly you mean by that and perhaps some examples?
Yeah, well, first, um, I don't want to be flagged as a Einstein hater. I love Einstein. He worked hard and all things like that. And I love Newton, even if it was not fully right. It was kind of incomplete. Um, there are things Einstein said that are right, but there are other things that he said are wrong or are
Perhaps not
impossible to
complete.
prove.
Right.
You know, so we'll never know, like wormholes, we'll never know about that because it's impossible to prove. And parallel universes and all that nonsense, it's um, it's impossible to prove. So we'll never know technically. So it's unprovable, you know. So, but there are things that are right, like time dilation is correct, gravitational time dilation and kinetic time dilation. That's fine, and that's what finite theory is based on. Actually, there was initially what it was based on. I was able to explain the whole universe based on time dilation. So I was able to explain perihelion precession disparity based on time dilation, the light bending, the galactic rotation curve, the expansion of the universe, and pretty much everything just based on time dilation. That's how it's all started. So mass increase and length contraction, I said, well, that's not necessary. You don't need that to explain the universe, because if you take the Newtonian dynamics, there's already light bending. So the acceleration of the gravity of the sun will already cause light bending. But if you add time dilation, it will double the effect of the light bending. So you don't need length contraction. You don't need a curved space-time to explain light bending. You know, you just add time dilation on top of Newtonian dynamics, and it's fine. Same thing with the perihelion precession disparity. And the same thing with the galactic rotation curve. But actually, the galactic rotation curve, what it is it's time dilation. It's two effects. It's actually time dilation, that the closer you get to the center of the galaxy, the time will actually dilate. Yeah, will dilate more and more to the point that everything will stop. So that's why you're gonna see. That's why the galactic rotation curve is kind of looks like that. If this is the radius here, the radius of the galaxy, then you're gonna see the galactic rotation curve going like that.
So very far away would be also coming down kind of to the point of the flatness of the graph, and then also at the very center of the galaxy as well. Is that kind of
the very center, the time is gonna stop. So the tangential velocity of the stars will come to a halt next to the black hole of the center of the galaxy. So they will not travel very fast, because the time dilation is extremely high. It's extremely concentrated.
Is that due to the amount of mass at the center of the galaxy being so high?
Due to the gravitational time dilation. So I take what Einstein says right there, that gravity dilates time and all that. So I don't invent anything. Again, I just apply the general relativity laws on the galactic rotation curve. But also, to replace dark matter, all you have to do is, because the galaxy's framework have their own spin. It's hard to explain, but the spin of the framework are also relative. There's no absolute framework. So there's no north, south, east, and west hard-coded in the galaxy. So, for example, if you have just let me ask you a simple question. If you have an empty universe with nothing in it, and you have a star in it, just one star. So the question is, can it spin so fast that it will eject plasma? If the star is empty,
there's nothing else in the
an
galaxy.
empty universe.
My gut wants to say no, because there wouldn't be any other mass to eject towards. But I don't know.
Yeah, the answer is correct, but the explanation is a little bit different.
Okay.
So no, the star cannot spin, because there's no framework. There's no absolute framework. The star creates its own framework You know what I mean? So it cannot eject plasma.
Could you
So
actually explain the absolute framework? And I believe there's also the parent framework as well, and how those are
yeah,
related.
exactly.
Okay.
So there's parent framework. There's to the point where there's the biggest mass in the galaxy is the one that defines the ultimate framework.
So
But
that'd be
if
the center
this
of the
might,
mass, the center of the galaxy, the black
yeah,
hole at the center of the
exactly,
galaxy. Okay.
yeah. But this mass itself cannot spin. Because it creates a framework. You know what I mean?
Right. So it's the reference point. So if
Yeah,
you're on the
exactly.
reference point, you're not going to be experiencing
It,
that acceleration of that spin.
exactly. So it's the same thing with galaxies. They slightly have their own framework because they're so massive that the framework of the galaxy have their own spin. So that affects the galactic rotation curve that's gonna create a shift in the velocity of the stars around the galaxy. So you don't need dark matter. You just need to add a little spin to the galaxy framework, and there you go.
And what
It's
you're
very
saying is
simple.
that it's not observable because we're within the reference, and that's why we don't notice it.
Um, well, if you talk about the Milky Way, it's different mathematics. But if we observe Andromeda galaxy, for example,
Hmm.
then it's easier to observe because we are outside the galaxy, you know.
I see. Okay.
But both galaxies are similar, but it's the same. It's all the same thing. We can see the galactic rotation curve, and the galaxy itself has its own spin, and that's what gives a higher inclination to the star velocities with far away from the center of the galaxy itself. So you don't need dark energies. Then it's the same thing with you don't need dark matter. So sorry, it's the same thing with dark energy. You don't need dark energy because there's time contraction. If you consider, if for example, if you have a boat with two friends, you're driving the three of you are driving on a lake in Colorado, something like that, and you're in the middle boat. The friend ahead of you is traveling 2 times faster than you, and the friend behind you is traveling half your speed. So you're gonna see you're gonna see the guy your friend ahead of you um getting away from you. You know, relative to you, you're gonna see him getting distance from you. Same thing with the your friend behind you.
Right.
So you're gonna see your friend behind you getting more and more distance behind your boat. But that's the same thing with galaxies. Galaxies are the universe is traveling in a much greater invisible universe in a gravitational potential. It's traveling within a gravitational potential created by a greater universe, and the galaxies are traveling at different speed because the gravitational potential for each galaxy is different. So the galaxy in front of us, we're seeing
Oh,
we're
it's
seeing
accelerating away. Right.
getting distant from us, and the same thing with the galaxy behind us. We see these galaxies getting away from us, but it's because we all have a different velocity, relative velocity, and we're traveling within a greater invisible universe. I've been saying that for a long time, and you can find a lot of articles saying that agreeing more and more than we are indeed within a bubble multiverse, that
Right.
our visible universe is lives within a much greater invisible universe, bubble multiverse. So I that was my hypothesis a long time ago, and now it's slowly tending towards that tangent.
I see. And so typically, if we were to extend the boat analogy, I'm not sure how far we can extend it, but basically what you're saying is that we're not necessarily aware that we're on the lake in the first place. And that's kind of what you're describing, is that we are on the
Yeah,
lake, right? So I'm curious, and maybe we can't take the analogy any further, but it's I'm interested in, obviously the boats they accelerate because they have motors. And so are you saying that the gravitational potential is kind of that motor, or what
yeah,
exactly is allowing those galaxies to be at different rates in the first place?
yeah. So time dilation creates an acceleration, and I'll show you the simple algebra that
Hmm.
I have right here later down the road, later today. Maybe I can show it right now if you wanna.
Certainly. That would be great.
Yeah. Um.
And so when we're talking about time dilation, as you're pulling this up, all we're really saying is that, for example, we have the need with our satellites to actually recalculate or be precise about the clocks that are on there because they're further from the mass of our planet. We actually have to
Yeah.
account for the change in time, although it's pretty minute at this distance. That's essentially what you're saying. Would that be accurate?
Yeah. Exactly.
Okay, that's
The
an
farther
example.
you are away from a mass, then the time rate will be greater. The
I
closer
see.
you are, the time rate will be slower.
Hmm. Okay.
And that time rate creates an acceleration. It creates a force because the speed changes. What is an acceleration is a delta V
Hmm.
on delta T. That's all it is. And since the time rate is changing, the speed is gonna change, and
Ah,
that's gonna be that's gonna be proportional to an acceleration. Acceleration is a force,
yeah.
so it's the same thing. Acceleration is a times mass equals force. So you just add a mass and you have a force. But I like to get things very simple
Hmm.
and simplify a force into an acceleration. So here's the evidence right here. The We can see here the acceleration. If we consider the speed, the initial speed to be zero, if we simplify this thing with the delta v with the initial speed to be zero minus the final speed, then we get this equation where epsilon is a small delta time, tf is the time dilated, t is the initial time, and p is the final position of the object. But if we consider p and epsilon to be units, and we just pay attention to the time dilation here, then we gonna get this curve. So that means the time dilation delta, the 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 shorter it is, the greater the acceleration will be. So
I see.
the slower the time is gonna the time rate is gonna go, the greater the acceleration is gonna be. So that makes a whole lot of sense. It's yeah, I figured it out this week. Somebody in APEC asked me to have the mathematical evidence, and here it is. It's a link between time dilation and acceleration, and you don't even need it's actually it encompasses Hamiltonians that encompasses uh, Newtonian laws like F equal ma and things like that. So it's very the a top level equation is very simple to understand. Um, the again the shorter the delta time dilation will be,
The
the
higher the
greater the
acceleration.
acceleration is it's gonna generate.
Okay.
So
Interesting.
yeah.
So how does that play into this concept of if we were to accelerate close to the speed of light, for example? What I understand is that's also kind of a form of time dilation in a way. Is that encompassed in this as well?
Um, so the acceleration that you're talking about kinetic acceleration, kinetic time dilation. Here I'm talking about gravitational time dilation.
Okay.
You're talking about kinetic time dilation. I need to come up with the right maths, but thanks for the thanks for the heads up. I'll need to work on that tonight.
Right, because it's kind of two sides of the same coin in a way, I would think,
Yeah, it's the same
is
thing.
right. You're experiencing the end result's kind of the same.
Yeah,
You're getting
it's energy.
right.
It's all it's all energy potential. So that's what finite theory. First, I started by my theory by explaining everything with time dilation, but then I recently figured that the energy potential, any form of energy potential, will create time dilation, will create acceleration and all that. Energy potential can be electromagnetic. It can be magnetic. It can be electric. It can be electromagnetic, and it can be gravito-electromagnetic as well.
Right.
So these are all forms of energy potential that you can use to create an acceleration. And the gravity, all it is, I don't invent anything. It's already it was already invented 100 years ago. You know, gravity, all it is, it's a gravito-electric force or gravito-electric energy potential, and there's also the gravito-magnetic energy potential that you can use that nature that we can harness that we can definitely harness
Mm-hmm.
to commercially, and we don't need like neutron stars or any astronomical masses to generate gravitomagnetic energy. It's much stronger than what relativity predicts, because general relativity is based on the Maxwell's equations that were tested like 200 years ago. The it's based on the magnetic permeability, which was measured like 200 years ago, a long time ago.
Mm-hmm.
And then we kind of tried to explain everything without testing the gravitomagnetic permeability. But the gravitomagnetic permeability is much stronger than what general relativity predicts.
Right.
Even if gravity pro B claims to have successfully measured it, which was wrong because there was a lot of noise in the gravity probe B testing, but they didn't want to admit that it was a failure, so they claimed it was a success, but it's not true because it was very expensive, so they didn't want to admit that they wasted all the taxpayers' money for nothing. But um,
Are you referencing the articles that I linked to you previous to our discussion, or are you referencing the measure of gravitational waves? I'm not
no, I'm
entirely
talking
clear.
about the gravity probe B, which was
Oh,
a
gravity probe B.
yes, some probe that was sent years ago to test the
Gotcha.
gravitomagnetic strength.
Okay, I see. I see.
Yeah,
So every theory is obviously just a theory until we have an experiment that we can use
yeah.
to test and validate it. And from reading your papers, I understand that you have some various thoughts on how one might actually go about doing so. Would you mind kind of breaking down those various thoughts and what sort of experiment would be necessary to test this hypothesis?
Yeah, I already started my own experiments here at home. I can maybe I can share them to you
Yeah, those
here.
videos were really cool. If you want to put those
Yeah.
on the screen, you're very
Okay.
welcome to do so.
Brief
And yeah, I
time.
want to definitely discuss because obviously the where I'm most fascinated is how can we bring this from our brains into hard real devices, mechanical things that we can actually utilize to build
Yeah.
spaceships at the end of the day.
Yeah.
Right.
So again, just before I present them to you, um, again, the gravito-magnetic energy potential can be created by spinning a disk very fast.
Mm-hmm.
It's like a charged disk. If you spin a charged disk very fast, then it's gonna create a magnetic field. Same thing with gravito-electric field. You spin it, which is just a mass in motion that you spin very fast. It's gonna induce a gravito-magnetic energy potential.
Okay.
So this is my first experiment that I did last year. Um, so which is a grinder, a simple grinder. I think I did that in November 2023. So I'll show you what my
And we'll have links to these videos as well for people that want to check this out themselves.
so I'll show it to you right now.
Mm-hmm.
So you can see when the disc is spinning very fast, the the mass, the weight of the grinder is is lower than at rest. So when the
Right.
disc stops spinning, then
Then it equals out again.
yeah, it equals out again. It goes back to normal. So I went to a conference in Washington D.C. where I met some PhD from Lockheed Martin. I showed him that. I showed him that, and he asked me to do it um, in a like more cleanly, like
Controlled.
using two balances,
Okay.
like we see right now, like a Harvard style OHAS balance here. So I'll show you what happens right now.
Have you been contacted by any other organizations that want to work with you for this type of thing?
Just one sec. I'm gonna show you what happens.
Okay.
So you see the weight is actually increasing when the disk is spinning,
I think you might
and
still be sharing.
it
You're still
stays
sharing
greater.
experiment 1 here. We're seeing experiment 1.1. You might need to switch the window that you're sharing.
Oh, sorry.
All good. Yeah, no worries.
I'm gonna share the screen again. Whoops. Sorry about that. Gonna share. I need to share each tab separately. Huh?
Yeah, you can do
Screen.
you can do your whole desktop, but sometimes you don't want to do that necessarily. So
Yeah. So here's the
okay,
second experiment.
cool.
Yeah, sorry about that. So
No worries. Okay. Oh, right.
you can see the weight is actually shifting again and
Hmm.
stays down. So it gains weight in that case.
Right.
And when the disc is stops spinning, then it goes back to normal.
So how do you
And
decide? How do you vary if it's going to increase its weight, its mass, or decrease its mass? And in this case, would mass and weight be equivalent words, or is there a nuance there that's important to note?
yeah, so I need to narrow that down. So initially, I That's a good question. I assume that the direction of the disk will determine whether the grinder would gain weight or lose weight.
Hmm.
But then I did the experiment with the disc, the grinder flipped upside down, and I still got a weight gain. But the grinder upside down was kind of there was a greater uncertainty because it's very far away from the disc. The disc was very farther away from the balance. So
And could you enlighten me as to why there are the two electrodes that are connecting to the plates? I see the red and the right and the white wires. How do those play into this? Is that the electric? Obviously, it's electric, but what's the purpose of that?
yeah, it's I had to replace um the button to activate the grinder to turn it
Ah,
on and off. So I kind of dismounted the grinder and I removed the safety the safety the level the handle and all that stuff, and I replaced it with a little button that I could just press,
right.
and I
Okay,
could remotely turn on and off the grinder.
I see.
Yeah, so it's just to facilitate the turning on and off the grinder here.
Okay.
Um,
So, is there anything special about this other than the high rates of rotation that we're able to achieve here? I basically see a grinder which is taped to the plate to ensure that it doesn't go flying away, and I see
yeah.
these wires which are sort of a way of turning on and off the system. What else would be important to note within this video?
Um, yeah, so you see the weight shifting, and I also put a a gravimeter. In the iPhone, you have a MEMS gravimeter, and you can measure the strength of the gravity. So I put the iPhone underneath the balance as well to confirm there was a gravity shift, and I did measure a gravity shift that to the same order of what I was expecting.
Okay,
So you don't see the iPhone under the balance here because that's not what it was this example was aimed for. But
sure.
I did put
That's substantial
the
though.
sorry.
That's really fascinating. Wow.
Yeah. So
And so this is just a conventional grinder with no bells and whistles other than the way to turn
yeah,
it on and off.
yeah, exactly. That's a standard grinder used for to cut steel. It goes at 7,000 RPM. So that's why I want to get one of those.
Would you have you considered trying this? I'm curious. I mean, it's difficult to get a vacuum at home, obviously, but perhaps in a vacuum or in water or in oil. I'm not sure how you'd totally facilitate such a test, but are those things that you've considered? Because for example, with the Byfield-Brown effect, a lot of the detractors of that will say, well, this is an ion wind, and I'm not saying that this what you're showcasing is ion wind, but obviously people are going to have a hard time with this, right? And so, what other thoughts would you have about ways that we could kind of control this experiment?
Well, I did another experiment I'm gonna show later here. It's kind of the chronological
I see.
sequence of my experiments, but
Cool.
I have three or four other ones to show it to you right now. So this is not the only one, but some people were saying that oh, the grinder maybe it's the wind or things like that that could create a weight shift. So
Hmm.
I reproduced the same experiment using a magnetohydrodynamics vortex of liquid metal to remove the potential errors
Right.
that people were claiming, and I get the same results. So I'm gonna show you that in
Okay.
the
Sweet.
next three videos. Um, so, and the other one here is this is an interferometer in magnet. I did create a little interferometer here at home, and I moved the magnet next to the laser, and we'll see what happens here. So you can clearly see
The laser is moving.
the laser is deflecting a little bit.
Right.
So I don't touch anything. I just move the laser next to I just move the magnet next to the laser without touching it, and you can see the laser being deflected. So that's part of my theory as well. Any form of energy potential will create an acceleration that will affect the light as well, and things like that. So that's another evidence. It can be reproduced by obviously that's not my it was made at home, so it's not in a professional lab, but it can be easily reproduced in a scientific lab, and you're gonna get the same results. So yeah, so a magnetic field is another form of energy potential, like I was saying before. So a lot of people say that magnets cannot deflect lasers or photons, but that's completely wrong right there. So you can find a lot of experiments on YouTube regarding that, but they're just they didn't do it with an interferometer, which is a million times more precise.
So this would kind of be a bending of light, and instead of a gravitational field, a magnetic field.
Yeah, so
Okay.
it's the same thing. Gravity is that's all it is. It's an energy potential that creates an acceleration, and
Right.
you can do the same. You can do the same with the gravitoelectric, which is gravitomagnetic, magnetic or electric field. So it's all the same. And
And
you
we
can
we know
also
that
with light.
gravity can impact light just based on the fact that we can see, for example, stars behind a black hole, for example. Would that be kind of an analog, a much larger one?
Yeah, it's just the Newtonian gravity can explain light bending. You
Right.
add time dilation, it doubles the light bending, and now I'm saying it's just any form of energy potential that creates an acceleration.
Hmm.
So I'm on top of the Hamiltonian, which is again explaining which is a top level explanation of the Newtonian acceleration. So um,
So in a way, what we're doing here is we're perhaps reinterpreting old physics in a way.
yeah, it's
Is
a
that
top
fair?
level explanation of old physics, which is extremely simple.
Okay.
It's extremely simple to understand for a high school graduate. And here I'm gonna show. So I showed you that the gravitomagnetic energy potential creates a shift in the weight. What it is just mass times acceleration. So you change the acceleration, you're gonna change the weight. So you don't change the mass, but you change the weight. You know
Mm.
what I mean?
Right. There's a
So
key difference there. Okay.
yeah.
Yeah.
So it's the same thing. It's the exact same thing with electromagnetic energy potential, electromagnetic energy potential that we see right here. So this is the Cavendish experiment, and we're gonna see what happens when we turn on the lights. So this is an experiment that is extremely sensitive to gravity, and we're gonna see what happens when we turn on and off the lights.
Yeah. When I watched this one previous to our interview, this was really incredible. So saran wrap to avoid any changes in, I guess, wind in this
Yeah.
case.
Sorry?
So is this what? Can you explain the purpose of the saran wrap one more
Yeah,
time?
so he's trying to eliminate experimental error
Mhm.
with the heat that the lights are gonna generate. So he puts a plexiglass and he wraps the lights um, with some plastic to so that there's no the heat will not interfere. So it's just purely electromagnetic energy potential right here.
Right.
So again, right here, when you turn on the light, you see the light is creating energy potential right here,
Right.
which attracts the rod, the Cavendish rod. So that's another proof that I'm on the right track. Well, I'm pretty much on the right track right here.
Mhm.
Um, but that's another form of electromagnetic energy potential is another form of energy potential, so it's valid as well. And finally, this is
Ah,
this is the magnetohydrodynamics vortex of liquid gallium right here. So I have a car battery charger that generates 120 amps DC that goes directly into the gallium.
mhm.
And the vortex here has two neodymium magnets underneath
To spin
the
it.
pl- the plastic the black plastic covers right here. And so when you have an electric current that goes through liquid metal and you have a magnetic field as well, that's gonna create a Lorentz force. The Lorentz force is gonna propel the gallium into a certain direction, either clockwise or
Following the left-hand
counterclockwise.
rule.
And the vortex of gallium is gonna induce a gravitomagnetic energy potential, and that's what we're measuring right here. So you see here, I turn on the electric current, and you can see the apparatus is the weight of the apparatus is shifting on the
Right.
right. So I'll show it again. See on the right, as soon as I turn on the current right here, the weight of the apparatus is shifting,
Yep. In this
and
case, the mass is increasing, or the weight is increasing. The mass would be staying the same.
yeah, exactly,
Okay.
and that's an improvement of the grinder experiment because there's no wind or anything like that. And also, I redid the experiment with the gallium at solid state. And when it's at solid state, there's no weight shift because the gallium is not moving. So the gallium is not moving. It's not inducing any gravitomagnetic energy potential, and the weight is not shifting at all. And I also redone the experiment with the polarity inverse, and I get a weight shift, weight gain as well. So we can see on the right right here the weight is increasing slightly. So um, I still need to narrow down the weight gain, weight shift, because my first experiment, my first grinder experiment, I was getting a weight loss when it was horizontal, when the normal of the disc was horizontal, and when it's vertical, then I get a weight gain. So I need to scale up the experiment in a university. I'm already in touch with University of Sherbrooke to do that,
Oh, cool.
to scale up the experiment in a professional lab. So, yeah, these are the experiments I want to share here.
Thank you, sir. That's incredible. I really appreciate that, Phil. And I'm absolutely confident that others are going to find that to be fascinating as I do. And
Yeah,
one thing, so you mentioned that there was a gentleman from Lockheed that you spoke to. Do you think that aspects of the black technology world or the classified technology world may have discovered these these aspects of physics perhaps as far back as 100 years or more ago? What's your understanding of what potential progress may have been made, not publicly, and because we're just now kind of getting to a point where we can actually start to test these things in the public. But
yeah.
yeah, what's your thoughts there? What are your thoughts there?
So, there's a lot of classified experiment that were most likely reverse engineered. I'm not saying there were UFOs or not, or I'm not gonna talk about the Philadelphia experiment or anything like that. But the
That's another
chances are pretty,
podcast.
yeah,
Yeah.
the chances are pretty high that they are UFOs or things they reverse engineered already. So maybe there's a TR3B as well that is
Yeah.
very similar to what I'm doing.
Yeah, I
Um,
actually have spoken to some people that, they seem to think that that's legitimate and they're involved in those organizations. Um, but yeah, a lot of this I think is direction away from the fact that humans are capable of pretty incredible stuff. Pointing
yeah,
all the fingers at ET is not necessary.
yeah. So there is more like the chances are the likeliness of having this technology is pretty high already, and obviously the PhD is not going to talk to me about it, um, because it's classified, or they have the skunk work project at Lockheed. They're not going to talk about. Also,
Right.
they might have reverse engineered it, and they have the TRTB and all that, but they don't have the full theory. They don't have. They cannot expand. They cannot expand. Maybe they have anti-gravity, but they cannot explain what happens, or they cannot expand the theory to new technologies. Like I do with my theory, I can not only do anti-gravity, but I expanded it to other technologies like energy teleportation, force fields, tractor beams, and things like that. So it's very simple. Force field is and tractor beams is a form of time dilation that freezes everything within that beam. So you just need a lot of energy to freeze everything within that beam. It's going to induce time dilation, which will freeze everything within that beam. So you're not going to be able to move. You're going to be completely trapped within that beam. So there's nothing you can do. So it's exactly like what you see in Star Trek. You're gonna freeze everything within that beam, and nothing within that beam can move. And the energy is extremely safe as well, because you don't need gamma rays to create a tractor beam. Or you can use radio waves, but of high density, to induce time dilation. The same thing with energy teleportation. Actually, that's what energy teleportation is. It's you convert high energy beam of low density into low energy beams of high density back and forth. So radio waves are extremely safe, travels through matter, and low frequency waves actually are extremely safe. It goes through matter, and it's not dangerous to humans at all, contrarily to gamma rays, which are extremely dangerous, can cause cancer and things like that. So all you have to do is you convert high energy waves of low density into low energy waves of high density back and forth, and That's all you have to do. And for tractor beams and force field, that's all it is. It's high some low energy waves of high density that will induce time dilation, which will freeze everything within that beam. So everything, all the movies you see, like Fire in the Sky with Travis Walton, and it's all true. It's all very easy, all true and very easy to understand. And you can do research on Travis Walton. He claims that the trees around the abduction area grew faster. So
Yeah.
and things
Very
like that.
familiar with that one, with that
Yeah.
case. Right.
So it's can be explained by time contraction and time dilation and all that. So it's of beam of high density can speed up or slow down the growth rate of anything nearby.
Right. So I'm curious, this is something that makes me, excited about the future for humanity, and the fact that people like yourself are researching this and not just writing down equations, but actually getting into our garages or wherever it may be and actually starting to test this means I think that we're on the right track towards finding or towards getting the ability for us to maybe commercialize these things down the road.
Yeah.
But obviously there is this aspect of what's going on where some of this, and we haven't touched on this necessarily, but there are, it seems like potentially individuals who already have unlocked some of these technologies. Maybe they don't know the theory behind them, but they're utilizing them anyways, right? I can use a power drill without knowing how it works. And that's a little scary. Also, the potential for what kinds of destructive capabilities would these also have is also probably potentially super high. So what is your outlook on the future for humanity with regard to these types of technologies, and how can we bring this to the public in a way that's going to be beneficial for people?
Yeah. So I believe a lot in constructive science versus destructive science, like creating bombs and things like that. It's all destructive science, and it's easy. It's not. There's no challenge. There's no challenge to create a bomb and blow up a whole city. There's nothing hard to do in that. Why are people doing that? I don't know. There's nothing hard in that. There's no challenge. So I have stronger beliefs in constructive science because it's a lot more challenging to do. It's a lot more difficult, and to create something constructive. It's easier to destruct versus constructing. So anyway, so there's a lot of so everything I've been talking about, anti-gravity, force field, tractor beams, energy teleportation, and all that, and it's all constructive. There's no way. I mean, it's not a it's not a way to kill people. You're not gonna kill people with a force field. You might freeze somebody, but you're not gonna kill him. I do have more dangerous equations, like the equivalence of a way to convert charge into energy, but that's destructive. But I don't focus on that. That doesn't really interests me that much. Or I don't focus also on vacuum energy, 0 point energy, and all that stuff, because I know there's not a lot of 0 point energy, but you can already teleport energy. So it's I don't spend time on things that are not been rational as well, or not, even if they're popular, or even if there's a lot of people that are obsessed with 0 point energy. I mean, there's no dark matter, so there's no what general relativity predicts as vacuum energy density. What they measure is not there. That's called the vacuum catastrophe. The the disparity between the theory and what they measure is a huge one of the biggest mistake in what the theory predicts. So I think there's the violet light catastrophe, but there's that's something else. But there's also the vacuum catastrophe, which is a huge blunder that the general relativity cannot cope with, and they just silently sweep that they were under the carpet. They just it's there, but people
Mhm.
still work on general relativity. I don't know why,
Right.
because people don't want to. It's a big political mess. The academia, the
Too many
mainstream, the
textbooks
Nobel
already written.
Prize. So
Too many
sorry.
books. There's too many books that have already been written on general relativity. We can't just. It's not going to be
Yeah,
profitable to just switch that up.
exactly. Why would if somebody with a PhD in astrophysics says that Einstein was wrong, he's gonna lose his credibility. He's not gonna be able to publish anymore. He's not gonna be able to win the Nobel Prize. Most likely gonna lose his job. He's gonna be like blacklisted as well. He's not even gonna be able to work at the McDonald's afterwards. It's
Right.
pretty, it's pretty, they are, very rude to these people, but that's the way it is. They don't talk about it. Me, I don't have a PhD in astrophysics, so I don't have anything to lose,
Right.
in that field, so that's why I don't care.
I really appreciate too your acknowledgement that there is the possibility for potentially destructive, highly destructive technologies. But I think we need more people like yourself who are pursuing the more difficult aspects of these and understanding ways that we can engineer this for the betterment of society. And
Yeah,
so I think that that's really what this is all about at the end of the day is promotion of those aspects of humanity. And I hope
yeah,
that can prevail in the long run.
yeah, definitely. And, I didn't patent my word because patent might imply political reasons for my patent to be rejected, and the government might own the patent actually. But and you can't patent nature's law. You can't patent nature's law. So it's so simple. My theory. I don't brag about having the most complex theory, but I'm gonna brag about the fact that it works. You
Certainly.
know, and it's
Yeah.
simple. Actually, it's gonna brag by the fact that the opposite actually, that it's simple and it works.
Right.
Yeah,
Yeah, I want to respect your time, man, and know that we're kind of a little bit past. But just to wrap things up here, I actually did have something that kind of jumped into my head as we were talking about the 0 point energy. So there's been a lot of talk about this effect known as the Casimir effect, and I was just curious if what your perspective on that would be, and does finite theory speak to what we're seeing with the Casimir effect in any way?
yeah. I didn't spend a lot of time on researching on the Casimir effect because it's not very scalable. It's hard to scale up.
Right.
The effect is there, but
Just so tiny, those
yeah,
plates
it's so
together.
tiny and it's very hard to scale up. So that's why I was not very interested. But there's a lot of colleagues at APEC that are working on that.
Yeah. Cool.
Yeah,
Right on, man. So obviously you mentioned that you're going to be doing some experiments with, I believe, the University of Sherwood and
Sherbrooke. Yeah.
Sherbrooke. What are the next steps for you besides that?
Um, yeah. So I'm an entrepreneur and I'm gonna try to commercialize all the technology and trying to get in touch with the Canadian National Research Center for that type of technology. So yeah, I was expecting an answer from them earlier, but I'm still waiting. But It's like the National Science Foundation in the United States. They're kind of similar.
Right.
So they're gonna help you with research that is kind of midway between theory and absolute completion.
Cool.
Yeah. So
Fantastic.
yeah, it's so yeah. Let's stay in touch.
Yeah, man. I'd love to have you back anytime you want to come on and talk about these fascinating topics.
Awesome. Yeah, I'll let you know in a couple of months where I'm at.
Fantastic. And just to wrap things up, where can people, obviously you have a YouTube channel, I'll be linking that information in the bottom of this video. Are there any other places that people could get in touch with you or find out more about what you're working on?
I have a book, a manuscript. I have a website called Fornux.com. It's Fornux, N like Nancy, X like Zidane. So Fornux.com. You can find my manuscript, my latest manuscript there. It's being rewritten by a PhD, by the way.
Oh, cool.
Yeah. I'm gonna apply for the Breakthrough Prize, which is the Nobel Prize. There are too many politics, so there you need to be.
Got to grease the right elbows for that one.
Yeah, the Nobel
Yeah.
Prize. You need to be to be nominated by a lot of people, and it depends on your country, and a lot of politics are involved. So I rather apply for the Breakthrough Prize. It's much simpler, and they give a lot more money also. So
Yeah, hopefully we can put that towards some more research. Lovely.
yeah, exactly.
Killer.
Yeah.
Well, thank you so much, Phil. This has been really incredible, and I always appreciate somebody who's willing to come on here and not just present their theory, but also present their experiments. So thank you again.
Awesome, and maybe we can come down to Colorado at some point.
Absolutely. You're welcome. It's a lovely
Awesome.
place.
All right.
All right. We'll be in touch, man. Thank you.
All right. Take care.